Pacific Rim University, National University of Singapore. Thank you. The time is yours.
Thank you very much, ladies and gentlemen, and for the introduction. I'll just acknowledge my co-authors, Christoph Matai and Colin Townsend, both at the University of Otago in New Zealand. Now, I'm talking to you today about multiple stresses in the context of this paper that came out in 2006 on the identification of 100 top ecological questions of high policy relevance in the UK. And two very prominent questions that arose out of this paper, which are not just limited to high policy relevance to the UK, but more broadly, one, what are the environmental consequences of farming practices if we consider that land use change to agriculture has been and continues to be the biggest or dominant driver of biodiversity change both in terrestrial and freshwater ecosystems. And secondly, in the context of climate change being the emerging dominant driver of biodiversity loss and changes in ecosystem functioning by the end of the century, is how these various drivers of climate change will interact with other stresses already impacting ecosystems and our ability to predict the consequences of those interactive effects. I should start by first defining what a stressor is, for those of you who are not ecologists in the audience. I define a stressor as a variable that, as a result of human activity, exceeds its range of normal variation and affects community composition and or ecosystem processes. One may assume that stressor effects always have negative effects, but this is not necessarily the case. It depends on the variable that you are measuring and also the values that you associate with that variable. Now, to give you a brief introduction into multiple stressor theory, when you have two or more factors that interact with each other, you can either have a simple outcome, in which case the effects of all stresses combined equals the sum of the individual effects. This is what we call an additive effect, and it's reasonably predictable as a consequence if you have knowledge of the individual effects. By contrast, a complex outcome is where the combined effects are smaller, we term this antagonistic, or larger, termed synergistic, than you would predict based on knowledge of single stressor effects. And there's a problem with complex outcomes or complex interactions, because if you can't predict them in an ecosystem, you have an ecological surprise as a consequence. Now, in a management perspective, managers want to know what the outcome of stresses are so that they can prioritise their management strategies and come up with the best approaches. So if they don't know the interactive effects of stresses, they may get it wrong as a consequence. So I'm going to put this in the context of the question of consequences of farming practices and farming intensification. Now, in New Zealand, intensification often originates from pristine tussock landscape and to high is a pristine condition, and under intensified land use, such as dairy farming, the land use changes as can be seen, and the stresses that are associated with this transition is increased loading of dissolved nutrients as a consequence of both runoff from the catchment and also increased fertilisation in the farming. There's an increase in deposited fine sediment reaching the stream bed. And then under a climate change scenario, as is expected for New Zealand, these are some of the emission scenarios, we have increased temperature as well. So to sum this up, what have we got? We've got three stresses. We've got hot, rich and dirty. What do you get? So in an attempt to unravel these interactive effects between these stresses, we have a number of approaches that we can use. One is to go out and to conduct a field survey and monitoring of the various streams that have the various stresses present. Now, this is very realistic, but it lacks control and doesn't enable us to disentangle what is actually having a cause and effect relationship. Another approach is to have a field experiment or a laboratory experiment. In the case of a field experiment, this is realistic, but it doesn't lack, it lacks control. And similarly, in a lab-based experiment, we can have a lot of control but very little realism. So as a compromise, we've conducted a mesocosm experiment, which is reasonably realistic, offering excellent control and a high degree of replication. And the system that we've used here is a system that I developed, which we've codenamed the Extreme system, the experimental stream system. And here we have header tanks, and this whole system is connected to the river immediately adjacent, so it has natural colonisation and drift, and it's a completely flow-through system where the water comes into these header tanks, and these are the stream mesocosms below, and these are hot water heaters that raise the temperature, being supplied by gas down in the bottom, right on it there. Now, the experimental methodology is 128 mesocosms, elevated nutrients, both nitrogen and phosphorus combined, and positive fine sediment, ambient and low, and warming across a temperature gradient between 0 and 6 degrees. That's 8 levels with 4 replicas of each treatment combination. So here you can see what the channels or mesocosms look like after 10 days. This is under control conditions with no stresses applied whatsoever. This is with nutrients added, this is with sediment added, and this is with both nutrients and sediment combined, and then these are also manipulated across that temperature gradient. The response variables that I'm going to present to you today are just 3 of over 70 response variables from the bacteria right up to the community and ecosystem metrics, but I'm going to present algal diversity as a measure of the Simpsons index diversity. I'm going to present EPT richness, EPT being an abbreviation for the orders of Ephemeroptera, Plecoptera and Trichoptera. This is the most commonly used stream health index used in biomonitoring when looking at macroinvertebrate communities in streams as indicators of stream health. And I'm going to present organic matter decomposition as an increasingly utilised functional measure of bacterial microbial processing. This is a functional process within a system that's very important to the delivery of energy, nutrients in a freshwater ecosystem. So, how does climate change warming interact with agricultural stresses? Here's an example of algal Simpsons diversity here, and as presented to you earlier, in the stream mesocosms, this is our control conditions, this is with nutrients, this is with sediment, and this is with both combined, and we have a temperature gradient from 0 to 6 degrees. And what you can immediately see here is that if you have no under control conditions and you increase temperature, you see a negative decline in biodiversity. If you just have sediment present, you actually see a positive increase in biodiversity. If you just have nutrients, you see a decline, and if you have both combined, you see an even stronger decline. So what's the take-home message here of this complexity? Well, the take-home message is that temperature rise may cause biodiversity to decline or increase depending on the sediment and or nutrient conditions present. If we then look how other response parameters responded, we see very different responses. This is EPT richness. And this is column strength loss. We see non-linear responses, and arrows are going all over the place in different directions. What's the take-home message here? It's that rising temperatures may have completely different consequences for measures of freshwater biodiversity and other measures commonly used that may worsen, improve, or remain the same depending on the sediment and or nutrient conditions present. Finally, when we put this in the context of our ability to predict the effects or the interactive effects of these 3 stresses, and across a temperature gradient in their prevalence of or complex outcomes, we see that of 72 response variables combined across that temperature gradient, you actually see a decrease in the number of additive responses. you see an increase in the rate of antagonistic responses and a weak increase in the number of synergistic responses as well. Collectively, the implications of this on our ability to predict the impact of multiple stresses is that multiple stresses effects may become increasingly difficult to predict on knowledge of single stressor effects as global warming intensifies. Thus, multiple stressor effects may alter species interactions and food web structure in unexpected ways, producing more frequent ecological surprises as temperatures rise. And from a management perspective, what we see is a shift in interactions between other stresses from the best case scenario of more additive effects at low temperatures, and under intensified climatic warming, we see a worst case for management, which is increased complex interactions and a decreased ability to predict those interactive effects. I would like to acknowledge the support of the many helpers of the Otago Stream team and also friends who have supported this research, and also acknowledge the New Zealand Foundation of Research, Science and Technology for their support in funding the research, and also the landowners. Thank you very much.
Okay, applause please. Very nice and interesting experiment, controlled experiment, right? Okay, maybe we proceed to the next presentation.